Well, thank you everybody for joining us. This is me, and Jorge is right next to me. We'll begin in 1 minute. We're just giving a chance for everybody to settle on our YouTube channel, as well as on our in our local platform that we're using for the webinars. Hey, George, how are you? Well, just to let you know, Jorge and I were both here located in South Florida. We're approximately 20 minutes just north of Miami, and I would dare to say, like, I don't know, 30 around 20 minutes west of Fort Lauderdale. That's where we're located. And just in case you were wondering, we had no problems with the hurricane that just passed, which was Dorian. So it everything went well. So we did everything went really well. So okay, let me just go ahead and hit the record button. That way we could begin. Jorge, give me 1 second. Okay. Well, thank you very much for joining us. Greatly appreciated that you will be participating in our webinar. My name is Edwin Robledo. I'm part of the Autodesk Eagle support team. And with us today also is Jorge Garcia, which is also part of our Eagle support team. And today the topic is a little bit beyond Eagle. We're going to talk about mainly electronics today. So we did part one, which was kind of like an introduction to signal quality integrity. And today we're doing part two, which Jorge has called physical basis for inductance and capacitance. I'm not really going to do much of an introduction in regards of what we're going to be covering because I think Jorge does a really good job at doing that himself, and we want to keep these as short as possible. Therefore, I'm going to go ahead and stop sharing my screen and let Jorge take over. If you have
Okay, excellent. So welcome everyone to this part 2 signal quality webinar. Now, I want to preface everything we're about to talk about by saying that this is a very big subject. By necessity, due to the time constraints, I'm going to gloss over a lot of details. The main goal is to give you something practical that you can work with when designing your PCBs. So I am going to, like I mentioned, there's going to be a lot of things that are either not mentioned or are going to be overly simplified. The main idea is just to start feeding some intuition. This is something that could be covered over many webinars uh, in detail. So just keep that in mind. If you notice a detail or something that I don't mention, it's simply because I'm just trying to give a very basic overview. Okay, so to start off, we do have to begin with a physical discussion about what the physical basis of inductance and capacitance is. And the reason for this is that I want to get you into the mindset of recognizing where a capacitor can be, or rather where capacitance effects can be observed, even though you haven't physically placed a capacitor there. So we want to look thinking beyond just components, but rather where the effect can be observed. So let's start off with capacitance. It's, in my opinion, the simpler one. And I've opened up Paint, and my goal with Paint is just to basically use it as a whiteboard. Okay. And the idea with capacitance is basically whenever you have two conductors. So there we go, brush. Okay, here's one. Okay, two conductors with some dielectric between them. Okay, so dielectric. Ah, give us a second just to close up shop over here. There we go. Okay. I'm doing this with a mouse, so it's not going to look pretty. Okay, whenever you have this scenario, you're going to be able to observe capacitance. Okay, and capacitance as an effect is simply the ability to store charge between two conductors. Okay, that's all it is the ability to store charge between two conductors. So keeping this in mind, you kind of get an idea of where the capacitor symbol comes from. So if we think about it, one thing that's kind of interesting is, let's say we have a little circuit over here. Okay. And this is an AC waveform, as I've indicated there. Okay. One thing we know is that current is always supposed to flow in a loop. Okay. So it seems really counterintuitive that current could, quote unquote, flow through a capacitor. Okay, because there's a space here. There's a break in the current. There's a break in the path. So this was something that initially perplexed James Clerk Maxwell, uh, the founder of electromagnetism. And basically, what ends up happening is that there isn't a current that flows through here, but there is an apparent, it appears to flow, because what's happening is whenever you have two uncharged plates and you connect a source such as this one, what's going to happen is that charges are going to accumulate. It's basically going to be moving charges on the positive cycle. It's going to move them from from the top plate to the bottom. Okay, so if we look at normal current flow, you have positive accumulating on top, and then you have negative accumulating on the bottom. Okay, and what's going to happen is, if this were a DC source, eventually enough charge accumulates to equal the voltage of the source, and then it behaves like an open circuit. But when you have an AC source, these charges are constantly flowing back and forth. Okay, there's no movement here in the middle. There's no current flow here in the middle. But it appears because of this interchange of charges going from top to bottom and from bottom to top. Okay, so wherever we see two conductors with anything separating them, anything non-conductive separating them, you can have a capacitor. You can think of it as a capacitor being there. Now, is it important? Is it going to affect your layout? That's going to depend on a lot of factors, and we're going to get to that in a second. But very quickly, I just wanted to cover this concept, the idea of having two conductors and how they can store charge between them. Okay? Now, let's talk about inductance. Whenever you have a conductor of any sort, okay, and we're going to, whoops, let's switch to pens. Okay, we're going to say that current is flowing this way through it. Okay? Whenever current is flowing through any conductor, this is going to induce magnetic field lines around that conductor. So I'm going to use a different color. And again, I'm going to draw these magnetic field lines. Okay. And again, you can just imagine an infinite number of these, kind of like as a density. Okay. And they're rotating. Now, how they're rotating, the definition you can use is, you'll see that in literature, there's something called the right-hand rule and the left-hand rule. Which one you use isn't important as long as you're consistent. Okay, so what you do is you align your thumb with the direction of current flow, which is this one over here. And then whatever direction your fingers curl in, that's the direction of rotation of the magnetic lines. Okay. No. Yeah, they're curling like this. So I have them. You have the arrows pointing down. I do, because they're coming like that. Okay, got it. Okay. So now basically induptance is the number of field lines that get generated per amp of current. That's all inductance is for however many amps I put here, how many field lines do I get? Depending on the conductor, you'll get more or less. Some conductors are very efficient or have a high inductance as an intrinsic property. Others have a lower inductance as an intrinsic property. But inductance is just that ratio, the number of field lines to the amps running through the conductor. Now, this is a very basic definition, okay, because what happens if we have another conductor running through here? Let me actually make that a different color, because what we can do, okay. I keep forgetting that I'm in eagle mode. Okay, and now I'll use the pencil. Okay, and let's say current is flowing, let's say the same way. Okay, and what's going to happen is, again, we have the same rings. Okay, and depending on the number of rings and how much current, there can be interaction between them. Okay, and this is what's known as mutual inductance. Now, one thing that maybe comes to mind is that whenever we're dealing with electricity, we're always talking about loops. So just a single floating wire segment like this isn't a real world scenario, but it helps us have understanding. That's why we discuss it. Okay? But keep that in mind. You're always, in the real world, you're going to be thinking about loops. And this concept of an interaction is very important. Okay, mutual inductance. So when you have traces near each other, they can couple to each other depending on how close they are and how much current they're running. Okay, so that's just the main concept we want to take from this. Okay, now I'm going to get a little mathy, but it'll just be one, I swear, just these two equations, and we're going to leave it at that. Okay, because we're almost getting to the part where we're going to be practical. So looking at the equations, we know that the equation for a capacitor that describes its voltage and current relationship is I, whoops, I'm still on this, I want it to be on this. Okay, back. Okay, I is equal to C dV dt. Okay, and then for the inductor, it's analogous. Okay, so it's V is equal to L, which is the inductance, di dt. Okay. Now, what's the key takeaway here from displaying these? Okay, first off, current through a capacitor is related to the voltage change. Okay, so a large voltage change will require a lot of current. Okay, a lot of that apparent current that we were talking about, that displacement current, as Maxwell called it. Okay, a small change in voltage, if the capacitance is small, will lead a small change in current. Now, one thing to keep in mind is that a capacitor is going to, because of this equation demonstrates, is going to resist changes in voltage. Okay, once it's going to put current out that's going to basically try to undo whatever voltage change it's experiencing. Okay, something similar happens with the inductor. Okay, it's going to maintain a current, but if there's suddenly a change, then it's going to produce a voltage that's going to try to resist that change. So those are the key takeaways from all of this. Be aware that inductance is simply number of field lines per amp of current running through the conductor. You can have interactions between nearby conductors because of these field lines overlapping. Okay, and from the equations from a capacitor and an inductor, we can see that in the case of a capacitor, it wants to resist any change in voltage, and it will basically allow a current to flow to counteract any change. And then in the case of an inductor, the same thing will happen. Any change in current is going to have a voltage produced is going to try to resist that change. And we're going to see why that's important in a second. Any questions about things so far? I'm sure there's a whole bunch. You know?
Actually, we've been doing okay. No, so far we've been doing okay, Jorge. The only comment was somebody was like, maybe for the formulas, just use the text command next time. That way we can see them.
I know, but it's like really, I can't get the nice symbols. I mean, granted,
I
I
kind of
can't,
like them. Yeah,
I can't draw the symbols nice either. So
I think you're doing just fine. It's
tell them
good.
that's a valid point. Okay.
We'll do.
So the final thing I wanted to show, and that's here on the inductance side, okay, is like we mentioned, current flows in loops. Okay, so we have current flowing this way. Okay, let's say then from there, it now goes down through the board, maybe through a via, and now it comes back to its source. Okay, so I'm going to switch to the pencil. So we have current flowing like this, then like this, and then like this. Okay, so left to right, top to bottom, then right to left, returning to the source. Okay, and I'm just going to draw an ambiguous circle here to be the source. Okay. And the reason I'm going over this part is because, as we mentioned before, you're going to have field lines. And again, following the rule, current, they circle this way. If you're looking at from left to right, they're going clockwise. But then these, because current is returning, are flowing in the opposite direction. Okay. So they're flowing this way. Now, why is this important? When electricity flows, as you guys know, in the DC case, electricity is looking for the path of least resistance. Okay. In the AC case, we're looking for the path of least impedance. Okay. In this case, you have whatever inductance the wire has itself minus the mutual inductance of the other one. And then you have the same thing happening here in reverse. So what ends up happening is that they end up canceling, they end up minimizing their impedance. And what this means is that on a PCB, even if you have a huge ground plane, the return current is going to try to follow the signal current as closely as it can. Because in doing so, it's going through the minimum impedance path. Okay, and it's because of this, because they end up canceling out their mutual inductance. Again, not perfectly. In real world, I'm glossing over the detail here. But you can kind of look at it in that way. They're subtracting from each other in their inductance. So in doing so, you get the path of least impedance. So that's the key thing to remember here. So I'm going to go ahead and do a quick little recap, and then we're going to jump into Eagle, showing how to apply these. Okay, for capacitors. And now I'm going to use a text command. Now I'm so going to use a text command. Okay, capacitors. They resist changes in voltage. Okay. Whenever you have two conductors separated by a dielectric, an insulator, you have a capacitor. Okay. Inductors. Inductors resist changes in current. Current. 2. The path of minimum impedance is when the return current can follow the signal current as closely as possible. Okay. So let's go ahead and go to Eagle now. And we're going to start with the inductive example. Okay. So here we have a really simple circuit. Okay, it's just a voltage divider. Okay. But we've taken into account the inductance of, let's say this is a through-hole resistor of its lead going into ground. Okay. 15 nanohenries is very small, but it's kind of within the ballpark of what you might expect a through-hole component to have on its leads as far as its inductance. Okay, and we've made this really simple source. It's just a pulse. Okay, and it's a 5 volt to 10 volt, so it has a DC offset of 7.5 volts. Okay, and what we're going to do is we're going to simulate what V out should be. Okay, now this one is a 1 megahertz square wave. Okay, so from 0 to 5 microseconds, that way we get 5 cycles. Oh, did I get the... There we go. Okay, now let me go ahead and just take out the ones we're interested in. We don't care about this. Apply. Well, VN just shows what's coming into the circuit. Okay, so VN, you can see 5 to 10, which is what we expect. And then we have here, because it's a voltage divider dividing everything by 2, we go 5 to 2.5 as expected. So everything looks as it should. Okay, and everything looks okay. And we'll talk a second about what's going on here. Okay, this is the voltage across the inductor. And you notice that it's basically not changing. Okay, so in a circuit like this, which is very typical, this is something you've done on a breadboard a billion times. Okay, the inductance of the lead of the component does nothing. It really is transparent and makes no changes. But let's say now we were to pass a high-speed signal through here. Okay, so we're going to go analog source setup, and I'll leave those values the same. But we're going to go ahead now and make this a lot faster. So we're going to turn this from a 1 megahertz square wave into a 1 gigahertz square wave with a really fast rise time. So 10 picosecond rise time, 10 picosecond fall time. I'll leave this like this, nano, nano. Okay. We're going to go over here. We obviously have to change this because if not, it will take forever to run. Okay, so what we've done is we've gone from a 1 megahertz square wave, which was completely transparent, went straight through, to a 1 gigahertz square wave. And you're going to see that things become very different. Woo! Let's clean this up so you guys can see what's going on. I hate that we always display that inductor. You guys already saw the input, but I'm going to leave it for now. We can change it later if we need to. Okay. So this one right here, this is the original square wave, the 5 to 10 volt square wave. Okay. And now on the output, we're getting all these peaks going on over here. Okay. So the output now, instead of going between 5 and 2.5 volts, is going from like 7.5 to 0. Okay, and if the circuit on the other end receiving this isn't ready for it, you're going to get some issues. Okay, because you can get some pretty nasty overvoltage conditions. And you can see that now the inductance is playing a very key role. It's resisting those changes in current that the circuit wants to do. Okay, and this is all governed by that equation we wrote over here earlier. Okay, if you solve the differential equation, you're going to see that this is expected behavior. The inductor changes its voltage to try to keep the current steady. And in doing so, you get these peaks. Okay, so we go from a circuit that was exactly as expected, exactly as designed at 1 megahertz and no surprises, to once you start going into higher frequency regimes, that inductance becomes important. And now you're getting this craziness.
Can you make this a little smaller? That way we can see the value change in the eagle itself on the probes.
If I do this thing,
Yeah, that's what I meant.
I like the graph better though.
I agree, but we have the capability of showing it there as
Right.
well. So I like to be able to provide them the option.
Excellent. Okay. Now this is what's known as ground bounce. Okay. And the key thing to realize here is that it's that voltage change that makes inductance important. If there wasn't this reaction by the inductor to try to maintain the current flow by changing its voltage, then it wouldn't create any problems. You wouldn't have any issues with inductance on PCBs. But because of this action, this reaction from the inductor to try to maintain current the same, you can run into issues like this. Okay, and again, this is a very simple example. Where basically, if you look, it's almost as if the DC offset changed a little bit. Okay. So let's go on now to an example using capacitors. Okay. Just so we can get a feel of why this is important. No, I want to keep it the way it was before. Okay. So here we have two conductors. Okay. And again, these are by unit length. I've just put in two sections. Obviously, I could put in many more. But just for the purpose of the example. And like we mentioned, if you have two conductors and there's a space between them, you have a capacitor. Okay. And again, these are per unit values. So if you look, okay, this is going to be a really simple waveform. We have this conductor that should have nothing on it. Okay. And then this is the one where we want our signal to get to. Okay. And again, this is just some impedance representing a load of some sort, whether it be the input of an op amp or whatever. So if we run it as is now, okay, this is a very slow square wave again. This one's I think 5 kilohertz square wave. Okay, and I go ahead and simulate that. And what you're going to see if we go to signals again, I'm going to take this off. Okay, you'll see that the input and output signals are basically identical. Okay, they're the same thing, which is what you would expect. Okay, and now the other conductor, because of that capacitive coupling, gets a little bit of stuff going on it, but not a big deal. Okay, most circuits wouldn't respond to this. So this would be a little bit of capacitive coupling, but you know, in most cases this would work. Okay, and the idea of showing you these low frequency examples is showing that because in many designs you're not dealing with hundreds of megahertz or gigahertz, you don't run into these types of effects, even though they're there, even though those intrinsic capacitors are there, those intrinsic inductors are there. At low frequencies, they're transparent. They don't really change things much. So that's why most of the circuits, maybe those of you who are in school or if you don't work in the high frequency regime, you never really think about these things. But it's good to be aware of them in case one day you are working with something a little bit faster and you see a weird effect, then you'll have an idea of why it's there. Now, as we did with the other one, let's go ahead and ramp up the frequency and see what happens. This one will not be pretty. Well, actually, it's kind of pretty, but it's not what you might expect. Okay, so we're going to speed this up basically to the same values we had before. 10 picos here, 10 pico here. This will become 0.5 nano, and this will become 1 nano. Okay. Again, we're going to go to 5 nano because otherwise it'll take forever. We hit simulate. And now if you look, let's take this one off and it'll make a lot of sense. Okay. You'll see that your input and output are exactly the same. But then you'll see that that victim line, that net that shouldn't have anything on it because we didn't put any type of load to it or any type of source, is getting basically the same signal with no DC offset. Okay, and that's because capacitors, as you guys know, clear any offset. Sorry, block DC. Let me get back to that. They block DC. Okay, so in your circuit, you're not expecting that nearby conductor to have an exact replica of your input signal. But that's what happens when you think about these effects and you see them taking place. Okay, so if you ever observe something weird in a layout or in a design that you weren't expecting, more than likely it's some capacitive or inductive effect that you haven't taken into account.
Can you put this a little smaller? That way we could see the effect of the probe in an eagle.
Mm-hmm. As you guys can see. So again, if that other conductor, you're not expecting it to have any type of signal on it, and this happens, your device, your product may totally malfunction. It may completely ignore it. It all depends on how you designed it. But this is definitely not something you're expecting. Okay. And again, I do need to mention I have glossed over some stuff here. Okay. There are other the term often uses parasitics. Some people don't like it because parasitics implies the idea that they're unintended or they aren't or they shouldn't be there. But the reality is that they are there. And if you don't take them into account, you can't predict the full behavior of your circuit. Okay. So this is just a really simple example of capacitive coupling. Okay. So that's what we wanted to show today. Again, the key takeaways back from the whiteboard. Okay, capacitors resist changes in voltage. Whenever you have two conductors separated by a dielectric, you're going to have a capacitor. Because they have this separation here, one thing I didn't mention earlier is that, or as you already know, if you just have DC, then it does become an open circuit and nothing flows. Okay, so capacitors block DC, but they allow the apparent displacement current when dealing with AC waveforms. Okay, in the case of inductors, you do have to worry about mutual inductance because the magnetic field lines can overlap. So you'll have the inductance of the wire itself plus any neighbors that are interacting with it. Simple rule of thumb, if you want to minimize inductive coupling, whatever the thickness of the traces is, make sure that that's the separation between them. Okay, simple rule of thumb. So if you have 10 mil traces, then you want to make sure that between any two traces, you have 10 mils of separation. In doing so, you can minimize any inductive coupling. Okay. Capacitive coupling in most PCB boards is not as big a concern. However, if it's something maybe an environmental situation where it meets extreme conditions, it gets gunk on it, that can affect, the conductivity between the two traces. Could do something there. But again, that's very far out. In the case of inductors, like we mentioned, they resist changes in current. They do so by producing a voltage that opposes that change in current. The larger the inductance, the larger the voltage generated in response to the same change. Okay, and current wants to follow the path of least impedance, and that path is always going to occur when it can follow the signal path closely. Okay, so keep that in mind when you're laying out your boards and you're doing your power planes. Try to leave them as solid as you can and try to route your traces in such a way that if you have anything sensitive, there's no return current path that may be running on the ground plane that could collide or interfere with yours, since that will create some additional noise. Okay. So any questions about any of this? I'm sure there are a lot. I'm expecting a
No, not
lot.
really so far. Are there any common scenarios of any type of particular circuitry where I could apply that you could tell us about a little examples of this type of circuits?
So again, most of the time you run into these things when you're dealing with high frequency, as both examples that I use show. So if you're in the hundreds of megahertz, heading up there, you need to start worrying about this stuff. So, Wi-Fi, anything related to Wi-Fi.
That's what I was thinking. Yeah, Wi-Fi.
Yeah, IoT. Now, the caveat to that is most people that do those types of products just buy the modules. Okay. So if you have like an ESP32 module or something like that,
So it comes
all
in
this
all one module.
craziness, has already been handled
It's
by the
already
module.
calculated for you. Okay.
Right. So you don't have to deal with it. But if you're rolling something your own or you're doing something specialized, then you do have to deal
I mean,
with
if
these
you
things.
are putting together your own product from scratch, I mean,
Correct.
yeah.
Correct. But again, that's not the typical. That's the 20%. 80% of people just grab the module and work on the other functionality that they
And
want to
then,
do.
of course, John, John being the
Yes.
high speed guru
Yes.
he is,
Correct me. Correct me.
he does have some comments to offer, and we appreciate it, John, that
Of
you do
course,
this
John.
every time. So you're more than welcome to. So John says, design your circuit to make parasitics to help you. Okay.
That's deep.
Also, it's deep. Yeah, that's really deep. Also, John suggests use microstrips for high frequency circuits. Want to tell us a little bit about microstrips, Jorge?
Yeah, so microstrips, the thing about the different topologies, those are the ones that are well understood. So you have microstrips, you have strip line, you have a few others. Basically, microstrip is when you have, and I'm going to go ahead and draw it because I can. So if you're looking at the thickness of the board, what you typically see with a microstrip is you'll see this is your trace, okay, because that copper, as thin as it is, does have a thickness. Okay, this is your board. Okay. This is the thickness of the board right there. And then right here, you have your copper plane on the bottom. Okay. So if I use, so let's use this right here is, I'm going to use text.
Yeah, it would be best to use some text to identify it.
Okay, ground. Let me just, okay. So right here. That's ground. Okay. That's the board thickness right there.
The electric?
FR4 typically. Let's make it a little bit wider. There we go. Okay. And then this right here is your signal trace. Okay. And the behavior of these types of topologies are well understood. So that's why he recommended microstrip. So you can, you're going to have how much coupling you can have to nearby traces. In something like this, those rules of thumb apply very well. So if you have two traces that are the same thickness and you don't want them to couple, then you just separate them by that amount.
That amount or more, or it has to be at least
No,
that
at
amount?
least that amount. Yeah, if it's
At least
more
that
than
amount or more. At least that amount. Okay. At
yeah.
least that amount. Well, I don't have any other questions on today's webinar.
Nothing on YouTube?
No, I'm checking on our YouTube channel. We do have a full class going on YouTube. But yeah, this was great. The concept is that we get many requests, not only of Eagle, but more within electronics and foundation of electronics. And today, Jorge wanted to provide the theory behind this and to prove that theory using the simulation capabilities of an eagle. That way, you have an understanding of what is the expected behavior and understand the results that you get in eagle. And that's the whole idea we want to. So so we're going to continue putting more of this content, as well as we're going to put more content regarding eagle in itself and how they use eagle as well. So I don't have any other questions other than John saying you have to terminate the microstrip in its characteristics of impedance.
Correct. And that's something we spoke about in the previous webinar. For best signal quality, you need to match impedances. Whatever
Always.
your termination or your load, you want it to be the same impedance as whatever the signal path is.
Yes, same rule happens when you're doing wiring. Same rules.
Yes, same rules.
Same rules happen when you're doing wiring. Okay.
We have a question here. 4 capacitor electrode pads on PCB. Electrode wire traces are connected to the IC, but the distance between IC pins are not wider than trace. I'm not sure what OnCar is asking. Distance between ICs are not wider than trace.
I think he's having the problem, or I think what he's trying to state is
about maybe the inductive coupling. Maybe that's what he's worried about.
and that the the distance between the pads itself.
Right, is not wider.
Exactly.
So again, you have to look at what type of signal is running through there. If it's not a high-speed signal, if you're not in the hundreds of megahertz, you'll get that scenario that I showed earlier, where the inactive trace, yeah, it shows a couple little blips, but it won't affect your signal much. It won't affect how the circuit behaves. So you'll get a little bit of it maybe, but it won't be anything to change how the circuit behaves. Okay, so remember, if you're not dealing with hundreds of megahertz, you're probably okay.
So we have a suggestion from somebody of our YouTube friends. Simulating piece pipe model scares me. So I need more of these tutorials. That's awesome. That's a great idea. Thanks for that, Sumit. That's awesome.
Yeah.
So yeah, I think I had my microphone off, but let me just tell it. So the comment was simulating P-Spice model scares me. We need more of these tutorials. I just thought that was a great comment.
And John brought up another good tip, one that our old auto router does automatically. Reduce coupling, keep adjacent traces at 90 degrees. Because if you do that, then the field lines can't interact. They're not in parallel. So you basically void inductive coupling altogether.
Well, I'd like to thank everybody for joining us today. It's been a great lesson, and we've been able, for those of you that already are experts, you're able to review this as well as put us on check to make sure. Any comments? Also, for those of us that are kind of new to electronics, we could use this as a foundation as we grow within the electronics industry. So, Cliff, thank you for the comments. Greatly appreciate it. And yes, this is recorded, so eventually it will make it to our YouTube page as well, to our YouTube channel as well. Everybody have a great day. And Jorge, thank you very much for your expertise and being able to simplify this for many of us that just maybe not have the experience, but are able to, broken down this way, have a better understanding of what we're covering. Thanks a lot, Jorge. Appreciate that.
Bye, everyone.
Everybody have a great day. Thank you.